Welcome to our presentation on planning multimodal exploratory actions for online robot attribute learning. My name is Xiaohan Zhang. This is joint work with Professor Jivko Sinapov from Tufts University and Professor Shiqi Zhang from SUNY Binghamton. We consider a common scenario where a robot is given a household object and asked to identify the object properties. For instance, in the query of is this object red and soft, words like red and soft are referred to as perceivable attributes. Objects may have many attributes like blue, full, and cylindrical. Some of these attributes that related to colors can be identified using vision-based methods, but other attributes like full and medium weight are not that straightforward. Robots need to take exploratory actions such as grasp, lift, and shake, coupled with different sensory modalities like audio and haptics to identify those attributes. However, robots don't know which actions are more useful for which attributes, and what makes it more complicated is that most actions have preconditions and costs. For example, action shake requires an object being in hand. As a result, the objective for robot attribute identification is to sequentially select exploratory actions while minimizing the total action cost. Robot attribute identification assumes the availability of a classifier psi. F is the streaming sensory data collected after performing action A, and P is the attribute to be identified. Given a multimodal exploration dataset, robot attribute learning algorithms can train the classifier psi. Existing works assume the dataset is provided beforehand, so they are considered offline. Offline robot attribute learning algorithms require large amounts of object exploration data, which is very expensive to collect. Thus, we focus on a novel online robot attribute learning setting, where the robot learns and identifies attributes at the same time. Formally defining robot attribute identification, offline and online attribute learning is the first contribution of our paper. Then we proposed an algorithm called information-theoretic reward shaping for online attribute learning. When asked, is this object red and soft, the robot will generate a perception model using psi on the specified attributes according to its prior knowledge. Queried attributes and the corresponding perception model then will be used to construct a POMDP framework for robot planning. The state space includes a set of fully observable states, indicating whether an action is successful or not, and another set of partially observable states, decided by the values of queried attributes. The robot uses the generated POMDP to compute a policy pi and interacts with the queried object. During the interaction, the robot augments its dataset using the data collected from its action executions. At the end of the trial, human will give feedback to label the perceived sensory data. In the standard POMDPs, observation and reward functions are independently developed. In our method, we dynamically shape the reward using the observation function as well as the robot's interaction experience. Fundamentally, our approach achieves the trade-off between exploration for attribute learning and exploitation for attribute identification. We designed the information-theoretic reward function based on environment rewards, perception model, and interaction experience. Details can be found in the paper. We demonstrated the learn action policy on a UR5E robot. The robot was given a task to identify if an object bottle is empty. This is a multicolored container half full of beans, so the answer should be no. At the beginning of the identification, the robot started with a uniform distribution, which means that it evenly believed that object can be empty or not. When in the early learning phase, the robot assumed that most actions were not useful due to the lack of sensory data. As a result, it sequentially executed action look, push, reignite, look, and push again according to the computed policy pi. However, pushing the object was not effective enough to identify empty, so the robot wrongly reported yes at the end of the trial. After multiple trials of interactions, the robot collected more sensory data that are labeled with empty or not empty, and the data can be used to train and improve the perception model for this attribute. When given the same task in the late learning phase, the generated policy suggested the robot take action look, grasp, lift, and shake 3 times sequentially. Compared to the taking action push, the robot now believes that shaking it can be more informative to tell whether it's empty or not. After completing the 6 actions, the belief finally converged to negative, and the robot reported no, which leads to a successful trial. To conclude, we formally defined 3 robot multimodal perception problems, including robot attribute identification, offline and online robot attribute learning. And we also developed an algorithm called information-theoretic reward shaping. Thank you for your attention.